Welcome to Train Signal. I'm Chris Bryant, CCIE number 12933, and this is video 14, BGP Part 2. And if you have, for some reason, skipped Part 1, you really should go back and watch that one first, because our study of path attributes actually carries over from the previous lesson. The path attributes that we're going to spend most of our time with in this lesson are the med and local pref. And we've got some excellent real-world examples for you here, some in-depth examples of how these two path attributes are used. Because not only are these two of the most commonly used path attributes, they're also the two that are most commonly confused with each other. You're going to have that nailed within 10 minutes. It's not complicated at all. You just need to be exposed to the situations where you would use both instead of just reading about them next to each other in a book. Because when you do that, and I have been there, it's a little confusing to keep them straight during exam time. But after this lecture, it'll be second nature to you. While we're doing that, I'm going to introduce you to the concept of route maps. And route maps are simply a series of match and set statements that do often use access lists as well in conjunction with them. Route maps are used primarily to change or assign BGP path attributes. When we do any kind of path attribute manipulation, we're probably going to do it with a route map. Following that discussion, we're going to talk about the wait path attribute. This is the first attribute in the BGP best path selection process. So if it's the first one, we need to know the details of it inside and out. We need to know all the defaults, and there's more than one. We need to know how to change it for a route. We need to know how to change it for a neighbor. And we're going to take a look at all those scenarios here today. I have listed the remaining path attributes as miscellaneous, but do not confuse that with unimportant, because they're not unimportant. We are not going to go into them in the depth that we've gone through local pref and med and wait and some of the other attributes from the other lesson. But they're still important. You need to know about them for the BSCI exam. You need to know about them if you're ever going to work with BGP in a production network. And you also need to be introduced to them now so you can master them down the road for your more advanced routing studies. And right after that, we're going to go into BGP Route Aggregation. And aggregation is simply the BGP term for summarization. This is route summarization. And even if you are familiar with the major command to aggregate routes in BGP, and I'm sure that you are very comfortable at this point with your route summarization skills, and if you're not, you need to get that way, and you'll get a chance here with some more examples. Don't skim this section thinking you know everything about BGP route aggregation. It's got some surprising defaults, and if you've never seen it before and you're brand new to it, you're going to be really surprised about what the default is for route aggregation in BGP as opposed to what it is for route summarization in the other lessons. So I hope that tease got your interest up, and you'll hang in there when we're doing BGP route aggregation. Finally, right at the end, we'll do a quick review of the difference between resetting and clearing a BGP connection. And you'll see me reset them during these lectures. You'll see me clear them. I do that on purpose just to show them both to you. And at the very tail end of this lecture, we'll take a quick look at the differences and similarities between the two. Having said that, let's get started with a discussion of the multi-exit discriminator. Sounds awfully familiar. It is the MED. And what this is, it's an optional BGP attribute. It doesn't have to be set. And it informs the AS receiving the value what path should be used to enter the AS that is sending it. And this value, the lowest MED, is preferred. And this is part of the confusion between the MED and the local pref, because it's actually the path with the highest local pref that will be preferred, but it's the one with the lowest MED that is preferred. Let's take a quick look at a possible network setup here where the MED would be used. In this scenario, AS100 is under our control. We really don't have anything to do with AS200. We have no access to router 3. But when packets come in, or BGP data comes in from router 3 or from AS200, I should say, we want it to take the path to R2. Perhaps that's a path with much higher bandwidth than the path to router 1. Maybe router 2 is a high-end router and router 1 is a low-end router. Because again, not all routers are created equal, and BGP is a hog when it comes to router resources. So for one of those two reasons, or possibly both, we want R3 to use the path into AS100 through R2 primarily. And what we can do here is send router 3 a different MED value from each router. Router 2 in this example is sending a MED of 100 and R1 is sending a MED of 200. This will influence the remote AS200, to then use the path advertising the lowest MED. And you know how you can keep that in mind, that it's the lowest value for this one? Because when we write route maps, and I'll bring a screen up here just to show you that. You haven't been introduced to full-blown route maps yet, but I'm going to show you just a real basic one here very quickly and show you how to remember that it's the lowest MED that is preferred. And actually the way that the router refers to it to begin with. We'll write a route map and call it set MED permit 10. Should always give route maps and access lists intuitive names, so when someone like me comes in behind you, I can look at it and tell what you were doing with it. And in this case, we're going to use the set command here, not use a match, and I'll use iOS help to bring up all the possible options. And again, don't panic yet. You don't have to know all these for the BSCI exam, but I bring this up mainly to show you that most of the values that you change with route maps are related to BGP. Here's an AS path command we could use. Here's a community list and a community, both BGP terms that you haven't seen yet. BGP route flap dampening parameters, extended community attribute in BGP. And here are a couple that you've at least heard of at this point. BGP local preference, we can set that. We can set the origin code, you've heard about that in the previous lesson. You could set the wait code. But how are we going to set the MED? Do you see anything in this column that says MED or multi-exit discriminator or anything? I don't see anything at all. So what we have to know, because the router really isn't giving us much of a hint, is that it is the metric that we are setting. When you want to change the MED with a route map, you use the metric option. And that's metric value for destination routing protocol. That's really not a very good description of the MED. As far as I'm concerned, it's not very intuitive. You cannot read that and say, oh yeah, that's the MED. But keep in mind that it would be the lowest value that's preferred because all our protocols prefer the lowest metric. Whether the metric is hop count, cost, or a composite, the lowest metric is always preferred. So that's a good way to keep that straight. That's why we use a MED, and the lowest MED is preferred. That's in comparison to our next path attribute, the local preference attribute. And what this does, and I put it in large capital letters there, not to yell at you, hey, local pref, but to show you that this is how you see it written in BGP documentation often. You see it that way in Cisco docs, you see it in non-Cisco docs, you see it in vendor-independent documents. So I just want you to get used to seeing it that way and not wonder, hey, what's this local underscore pref? Is that the attribute? Yes, it is. That's what they're talking about. The local preference attribute informs routers within the local AS what path they should use to exit that AS. The local preference value is passed only among IBGP peers, which makes perfect sense. There's no reason for a router in another AS to see the local preference value of the local AS. It never leaves the local autonomous system under any circumstances. You literally can't do it. And what we're going to look at here is an example similar to the network. Actually, it's just like the network we just looked at, except we've taken the MED arrows out. Because in this scenario, what we could be looking at is a situation, again, where we're in control of AS100, and we want all the data leaving the AS to go over the link between router 2 and router 3. So it's the same kind of thing. We want to use the same link, but where the MED was controlling how the data came into AS100, the local preference is affecting how what path it takes to leave. So what we would do is set a local preference for the paths as they left at R2 with a higher local preference. So the routes being advertised by R1 in the AS would have a local preference, say, of 100, which is the default, by the way. And we could double that on R2, set the local preference for all routes that R2 advertises to 200, and then all the BGP routes advertised by R2 would be preferred over those advertised by R1, and then that way it's going to leave via the link between 2 and 3. So that's how we use the MED. And to get first-hand knowledge of how to use these two values, I've reconfigured the network from the last lesson, and I'll bring up a network diagram in just a moment showing you what we've done. But here are just a few notes at the bottom of the whiteboard regarding this local preference and MED lab, because we're actually going to do them both. And what we're going to do, router 1, I've created multiple loopbacks on there, and you'll see the network numbers when we bring the routers up. It's advertising 6 of its loopbacks into the BGP domain. And let me go ahead and bring that up so you can see all this work. Excuse me, I skipped it there. There we go. Router 1 is in AS1 all by itself, and the dotted lines represent peer relationships in this network. So R1 has BGP adjacencies with R2 and R3, and they're going through the frame. And routers 2 and 3 each also have adjacencies to router 4. They're all found off a single Ethernet segment. And they are all in AS234. So those are our adjacencies for this particular network. And what we're going to do here is call the rack back up, call the routers back up. And we're going to take a quick look at the configuration, the current configuration of router 1, just so you can see what I've done here. You see all the extra loopbacks we've added since the last lesson, and that's a pretty big BGP configuration, but here's what we've got. It's still very simple. In AS1, that's what the number refers to there. I have no synchronization running. We will address the synchronization role in the next video, but it's something we have to configure now in order for these labs to function properly, and you will see why. We've got 6 network statements. We're advertising 6 loopbacks into BGP, and there are the 2 neighbor statements. And at this point, those are the only networks being advertised into BGP. So we're going to go down to router 4, and you may want to jot this down actually just on a notepad there next to your laptop. You can note that we're going to go down to router 4 and take a look at the BGP routing table. And just think, before we do this, see if you think from your knowledge that you picked up in the previous video, do you think that router 4 is going to have those loopbacks? Do you think it's going to see them? Are they going to be valid? Let's take a look. We're going to go down to router 4 and run show IP BGP. Well, they're all there. As a matter of fact, a lot of them are there. And we've got an interesting set of next hops there. 172.12.123.1, which is router 1's serial interface. That's the next hop IP address. Just move that up a bit. So we've got something interesting going on there. Do you know, first off, applying your knowledge from the previous lesson, why that next hop is the same for both of those, all those routes? Let's look at show IP BGP 1111. This is the command that we're always coming back to that really opens our eyes about things. And right now, you can see we've got some kind of problem because we've got this big word inaccessible here, and you know that's never good. Inaccessible is never good. And unfortunately for us, we've got them on both. But first off, let's just step back in time just a bit here. Here's the advertisement for this network coming from 23.2, which is router 2. The next hop, though, is router 1's serial interface. On the route coming from router 3, 23.3, it's the same thing. It's router 1's serial interface. Why? This is the kind of thing we have to be able to answer on the exam and in troubleshooting. Why is that? It's because router 2 and router 3 are learning about that network 1.1.1.1 and all of those loopbacks via an EBGP peer. And then the routes are being advertised to an IBGP peer. Remember, that's the exact scenario where the next hop IP address is going to stay the same. It's going to be retained. And actually, that's part of our problem right now. Because you can see this next hop IP address, or actually, do we have a problem? Because we see inaccessible here, but when I looked at the BGP table, all the routes are here. And look, I mean, all the asterisks are here. The asterisk indicates a valid route. Is there a problem? Do we care that this is inaccessible? Yeah, we care a lot that it's inaccessible, because that is the problem. So if that's a problem, then why are those paths showing as valid? They are showing as valid, but there is no arrowhead in front of any of them. Common BGP misconception is that if you see a route and it's got an asterisk next to it, it's ready to use. No, it's not. You've got to have a route selected as the best route. That's why, you may be tired of hearing it already at this point in our BGP studies, but that's why I keep coming back to show IP BGP and then putting the network number behind it. Because while show IP BGP will give you some path attribute information, and it'll show you which path has been selected as best, this is where you really see what's going on. Because you can see right here, it says paths 2 available, but there's no best path. The problem here is that router 4 has no idea where this next hop is, because we're not running an interior gateway protocol. If we try to ping 172.12.123.1 from right there, the only thing we get is a chance to practice our ping escape sequence. Control-Shift-6, Control-Shift-6. So we've got our initial problem right away, and you've already done some troubleshooting. Nice work. We've already done some troubleshooting in our initial configuration, because this looks like it would be so simple, and you see those asterisks and you think, well, we have no problem. But you run the right command and you see that you do have a problem. So what's our solution going to be? We're going to go to routers 2 and 3 and have them announce themselves to router 4 as the next hop for those routes. And we do that with the next hop self command. We're going to go to router 2 first. We've got to do it on 2 and 3. And we're in BGP AS234. Try that again. There we go. Neighbor 172.12.23.4. And remember, you don't have to know all this for the BSCI exam yet, but I want to show you that in the middle of all this, there is a next hop self command, and we chatted about this earlier in the earlier lesson about what the next hop calculation is and what's being disabled. Now you know. You've got to keep in mind, if a router learns about a route from an EBGP peer and then advertises it to an IBGP peer, the next hop IP address value is retained. So let's put next hop self there. try a soft reconfig there. And we're going to go to 3 and run the exact same command. Neighbor 172.12 for next hop self. Remember, a router can't announce to itself that it's its own next hop. It doesn't work that way. Let's go down to router 4, see what our table looks like. And now it looks totally different. Now we're in business because you see some arrowheads in the left-hand column. And now the next hops that we see are 23.2 and 23.3 respectively for every single route. And since router 4 is on that same segment, since that's the address found on the router 2 and 3's Ethernet interfaces, then you know it's accessible. We'll look at it anyway. We'll look at router 1. And you can see now that it says 2 available paths, but now one has been chosen as the best, the top path. You can see that they're all valid. We see some defaults. There's the med. See, it's even referred to as metric here. The med is 0. That's the default. The local pref is 100. That's the default. Valid, internal, and best. That's what we're looking for. We could run this command for every single one of these loopbacks, and the results are going to be a lot like this, because 172.12.23.2 will be the next hop IP address for all the remote loopbacks. Now what we're going to do, though, maybe we have a scenario where we want router 3 to be the next hop IP address, or the preferred address, or the preferred path, I should say, for all routes coming in from R1. If we do that, we don't have to write an access list, but we are going to write our first route map. And let's take a look at how we do that. We're going to go to router 3, and we need to write a route map to adjust the local preference of all routes coming in from router 1. We're not going to change the weight, we're going to change the local pref. So let's go to router 3. And here's the syntax for a route map. You just simply start with the route map command. Then you've got to give it a name. You do not have to give it as long a name as I do, but you should give it some kind of intuitive name. And we've got permit and denies that we can assign. And we're going to do a permit here. And we're going to give it the number 10. We are not going to use an access list here. If we wanted to just match specific routes coming in from R1, we'd write an ACL naming those routes, and then here we would put something like match IP address 5 if the ACL number was 5. But we're not going to do that here, and it's a popular misconception that you have to have a match statement in a route map clause, and you do not. We're not going to do that here. And remember all those set commands, set values that we had? One of them is local preference. So we're going to use this route map to set the local preference. We're going to double it to 200. Now we've got to apply it to the neighbor. So we're going to go ahead and enter the BGP AS process there, BGP 234. And we're going to start with the neighbor command. We're going to identify the neighbor. If I can get that, there we go, 172.12.123.1. Now we've got a lot more options here, as you recall. And the one we're going to use is the one at the very bottom of that, right above the word more, route map. Apply route map to neighbor. This route map is going to be applied to a neighbor, not to an interface. Now we've got to name what route map it is. And you know, there's one more thing we got to do. We have to specify whether the map is going to be applied to incoming routes or outbound routes. So this is quite a long neighbor command. Good syntax to keep in mind for your exam as well. But this is how we apply a route map to a neighbor. So now all the routes coming in from that neighbor are going to be run against that route map. Now let's take a look here. Let's show route map. The set med is the example we wrote earlier, so we're not paying any attention to that. But anytime you want to see what route maps already exist on a router, just run the command show route map. We will talk about route maps and policy routing in a later video. But right now we have no match clauses, so everything coming in is going to have a local pref of 200 set. Let's run show IP BGP and see if it took effect. It did not take effect without a clear. So we're going to reset the, refresh the connections, I should say. I'm going to try a soft reset. It says inbound soft reconfig for 23.4 not possible. We don't care about that because we're caring about the routes coming in from 1. But I want you to see that because not every router in the world is the latest and the greatest. This one has an iOS version. It's like 12.2.1, and it does not recognize inbound soft reconfigs. I'm definitely not showing you an old iOS. I just want to make that clear. But I did find one where it doesn't support this feature. Because you could see that in the real world and say, I wonder why. The iOS doesn't support it. Let's run show IP route, show IP BGP. And now you see under the local pref column that the local preference has been set to 200 for all routes coming in for router 1. So let's go down to router 4 and see what the impact of that is. The impact is that you can see that every single destination, just looking at the top one for 1.1.1.1, you can see that the local preference value has been successfully changed on the route with the next hop of 23.3. It's been changed to 200. It's been changed to 200 for all of them. So since the BGP path selection process uses weight first, that's a tie because we didn't change any weights. They're all 0 by default here. So the next choice, the next criteria is local preference. And since these have a higher, the paths with a higher local preference are being preferred over the ones that it was previously using. So just that quickly then, you see that we were able to change the local preference pretty easily. Took one command, took a long command, did a soft refresh, and now we have totally changed router 4's path selection. Now, where it was taking the path through router 2 to then go up to router 1 and the loopbacks on router 1, we changed the local preference at 3. That local preference was carried in the adds to 4, and now 4 is using that path. Now, let's take a look then at router 2's BGP table. I'll show you a new concept here that we're going to explore a little more in the next video. But bringing that back up then for a moment, let's take a look at the route advertisements here and what's going on. Router 2 may be getting routes from router 4. Don't you think? I mean, there's a peering relationship there. So what we need to look at, did changing the local preference on router 3 change the local preference of the routes we're going to see on router 2? Because remember when we talked about local preference, that value is carried throughout the autonomous system. What do you think? You can come up with an answer there while we take a look at what's going on here. Sure didn't. We see nothing there under local preference, and you can see that the route that is being selected for each one of the loopbacks in question has the next hop of 123.1, which would make sense just looking at it, because it would seem nonsensical for router 2 to go through the Ethernet to 4, then back out to 3, and then up to 1, or even through the Ethernet to 3 and back up to 1. That wouldn't make much sense. But we've always got to take it to the next level. We've got to know why. Let's do a show IP BGP for that first loopback. There's only one path here. Notice where it says paths 1 available. Well, that makes the path selection pretty easy. But why then, if router 2 has a peering relationship with router 4, and it does, why isn't router 4 advertising routes to router 2? There's a rule with BGP that a route received from one IBGP neighbor cannot be advertised to another IBGP neighbor. That's where route reflectors come in. You've probably read about those or at least heard about them if you've done any BGP reading at all. And route reflectors are covered in the 3rd BGP video. But I wanted to show this particular BGP rule to you now so you'd understand why router 2's routes are all showing an AS of 100. Excuse me, a local preference of 100. When we changed it over on router 3 and they're in the same AS. It's because router 4 is not sending any routes to router 2. Again, an IBGP neighbor sends a route to another IBGP neighbor. That neighbor cannot then advertise it to another IBGP neighbor. It's one of those things where you say it and it sounds confusing, but when you see it in action, it's very simple. So we're going to take a look at how to combat that issue or combat that rule with route reflectors in a future video. But I wanted you to see that now. Now, what's more likely, though, in a skill you must have for the exam and the workplace? What if we wanted router 4 to use the path through R3 only if the remote destination is 1.1.1.1, but for all the other loopbacks to go through R2 like it was doing originally? That's the kind of thing we end up doing in the workplace. You're not going to have too many situations where you just say, oh, okay, we're just going to change the local pref for all 300 routes. That's not going to work. And the exam is probably going to ask you, what would you do if you just wanted one of these paths to have a different local preference? We're going to do something very similar to what we did with the route map, but we've got to bring in an access list. But what we're going to do first is go on to router 4 and take off that, to router 3 and take that route map off. We're kind of starting from scratch here. And you've always got to know how to take commands off. And again, up arrow, Control A to go to the front of the line, just type no and a space, and it's gone already. Can't beat that. We're going to go ahead and take the route map off too, just to stay in the habit of always cleaning up after ourselves when we're removing something. I hate that console message sometimes. And we saw the show route map command earlier. The route map was called preferred path, and to remove that, it's no route map, and then just follow it with the name. That's how we take a route map off. We'll run the command show route map. I'll run it again here so you can see it. And the only one we've got is set med. That's the example we used very early, and we'll go ahead and take that off too. Don't do half the job. Don't take the route map off a neighbor and then leave it on the router. So now we've taken that off, we've taken the neighbor statement off, and we're going to clear the BGP processor, actually just refresh it here in a moment. As soon as it gets done with its write. That's just a good habit to get into in your home lab as well. Just do a WR every time you leave a router, and you never have to worry about, hey, did I save my work? So let's take a look at router 4's BGP table at this point. See what we see. You can see that all the local prefs have gone back to 100 because we took the route map off the neighbor. And you can see also now that router 4 is using router 2 as the next hop IP address for all 6 of those loopbacks. So now we're going to fix it so that router 4 will use router 3 as the next hop to reach the first loopback, the all ones loopback, if you will, and continue to use R2 as the next hop for the other 5. That's where we're going to separate ourselves on exam day. Going to do very, very well. First thing we do is write an access list. Well, let's make it access list 17. But you know what you always do in a production network before you write an access list? You know what you always do? Make sure you don't have any. Or you'll probably have some, but you need to look at the numbers. We have no ACLs here. I knew we didn't have any ACLs, but again, that's a really good habit to get into. And especially if you go on and tackle the IE lab, you need to get in that habit. So we're going to write an access list 17 just because we get tired of writing access list 1 all the time, right? You remember the syntax of this. The host keyword means that the only address that matches the statement is 1.1.1.1. But we're going to leave it at that. And don't forget our implicit deny there, of course. So we're going to leave it at that and now start writing the route map. And I'm going to give it a kind of a long name here. Forgive me. This is the one we're preferring for network 1, so that's what I'm writing. Now I'm going to use a match statement. Match IP address 17. So when the route map hits that line, it's going to say, okay, go out and get access list 17. And every single address that matches that, we are going to set the local preference to 200. So far, so good. Now we're going to add another statement and spell it correctly. Always important. Permit 20. We're going to leave that one blank. We're going to leave that one blank because this is what's going to happen or be applied to every route that doesn't match the first route map statement. And the net effect is nothing. We don't want anything to happen to the routes that don't match that first ACL that we wrote. We want those to remain unchanged and untouched. Now comes the good part. We get to apply this monster to neighbor 172.12.123.1. There's the route map command. Prefer for network 1 in. I know that's a long route map, but the longer you work with Cisco technologies, the farther you climb the Cisco certification ladder and the job ladder, you will thank me one day for getting you to write descriptive route names. We're going to do a soft reset. And then we're going to do a save and go down to router 4 at this point and see what the situation is. Well, I'll tell you what, let's go back to 3 first, though. You should check the routing table there, the BGP table. And as soon as it finishes saving, you never mind waiting for a save because it's better to save too often than not at all. Because you know, occasionally somebody does kick a power cable out, or occasionally the iOS just goes nuts. So save your work. Let's look at show IP BGP. Notice this time that the local preference has only changed for the network that we named in the ACL. Isn't that cool? I mean, that's really great stuff. This is where you separate yourselves from the wannabes, when you can do something like this. And you can't. This is where you want to be. We knew how to identify the one route that we wanted to go through router 3. You knew how to do it with the local pref command. You wrote an access list, you wrote a route map, you applied it to the incoming routes. Now we're going to go down to router 4 and take a look at the BGP table. And you see now that only one local preference has changed. That's what we expected. It's for the all ones loopback, and it is indeed using 23.3 as the next hop for that particular network. The next hop for all the other networks, the ones with the arrowheads next to them, have 23.2 as the next hop IP address. That's the level of BGP path manipulation, path attribute manipulation you want to be at. That's how you get things done. So we've now used the local pref to apply it, change it for all the routes that were coming in, and we also used it for a single route, and that's as good as it gets. Well, let's take a look at that map again, because there may be another angle we want to look at this with. The local preference attribute, we used that in AS234 to tell other routers, here's what path you should choose when multiple valid paths exist to destination X. But what if we want to influence R1's path selection when choosing a path to enter AS234? That's where the MED comes in, because R1 has two possible entry points into AS234, router 2 and router 3. And to illustrate this, we're now going to go to router 4 and advertise its loopback. Let's check its loopbacks. We do have one loopback there, and that's the one that we're going to advertise. So we'll go into BGP 234 network, and we're going to name it all the way, just like we have on the router. And there's the mask statement. Let's see if we can do a soft reset here. Yep, looks good. Now again, things don't work as quickly in BGP when it comes to these routes, and we don't see R4s yet. Do we have any kind of next hop problem, you think? Probably not. And we don't, because there's the route. And just as a reminder from something we said earlier, like I said, whenever we see zeros for all 4 octets, I think everybody still instinctively panics just a little bit and says, hey, how'd that get there? You may see them in frame relay inverse ARP statements. Of course, we use them in, we use a lot of zeros when we're writing static default routes. But these next hops of 0, 0, 0, 0 are fine, because you'll notice that they're only next to the routes that are locally originated. You'll also note that the weight for those paths is 32,768. That is the default for a path that is locally originated. But now we do see 2 paths to router 4's loopback, the all 4's loopback. The next hops were certainly accessible, so there was no problem there. There's no need for the next hop self command. You see the default weight, you see what the AS path is, and you see that it has selected 123.2 as the next hop to enter AS234. And we could put 50 loopbacks on router 4 and advertise them all up here, and 123.2 is going to remain the next hop IP address for them. Now, what if we're in a scenario where AS234 is under our administrative control, and we want router 1 to use router 3 as the next hop instead of router 2? That's where the MED comes in. The multi-exit discriminator is used to inform another autonomous system of the preferred path into the local autonomous system. And reminder that it is the lowest MED that's the preferred next hop, because it's a metric, and the lowest metric is always preferred. So what we're going to do first is go to router 2 and write a route map that's going to set a metric of 200 for all outbound routes. No need for a route map, an access list here, but we are definitely going to need a route map. We'll call it set med 200, permit 10. We don't need a match statement because we're applying this to all routes. Set the metric to 200. That's all we need to do, because since we didn't put a match statement in, all routes are going to match this clause. Now we'll go into the BGP process, router BGP 234. We use the neighbor command, 172.12.123.1. We're going to apply the route map, set med 200, And on the exam or in the real world, don't forget, you've got to apply the direction of the route map. We're going to go to router 3 and do close to the same thing, but we're going to set a metric of 100. Set med 100, permit 10. We're going to set the metric to 100. Again, since we didn't use a match statement, all routes will match this clause. We don't need to add another one. And we're going to go into the BGP process and apply that to the neighbor the same way we did it on router 2. So we've completed that. We'll do a quick WR there. And we're going to go up to router 1 in the meantime and check the BGP table. We don't see a changed metric yet, but we will after we do a soft reconfig. And you see now we've assigned metrics successfully. You see the metrics in the metric column. And you also see that 123.3 is now the next hop IP address to reach 4.4.4.4 because it has a lower metric. And there would have been no problem with us putting even more loopbacks on. We could have used an access list just like we did to change the local pref for one route while not changing it for all the routes. We could have done that as well. But the key here is this will really help you remember where we apply the med, why we apply it. The lowest med is going to be the path that is selected, where with the local pref value, the highest is preferred. So no matter if we were trying to affect how traffic leaves the AS or how traffic enters the AS, we can control the path that data takes as long as we use the correct command to do so. And now that we've taken an in-depth look at how we can use the med value, which is our metric in BGP, how we can use the local pref attribute to influence path selection, let's look for a moment at the primary way to do that, and that's with the weight attribute. This Cisco proprietary BGP attribute is the first attribute considered in the BGP best path selection process, unless of course the network is multi-vendor, in which case the weight is not considered at all. Weights can be changed on a per route or per neighbor basis, and generally you're going to change these on a per neighbor basis. But we're going to look at both. And with the defaults, there are some odd defaults here you just have to get used to. The first one is actually 32,768, and that is the default for a locally originated route, where 0 is for routes learned from other routers. So let's take a look at a couple of BGP tables that we've been working so far in this course. This is router 1, and right where we left off with the metrics being changed. And you see two different weights in the weight column there on the right-hand side, 32,768 and 0. And the weights for all the routes that were locally originated, that is, this is the router where the network command was used to introduce these networks into BGP, they have weights of 32,768. And we see that the routes learned from other destinations, in this instance the two paths to router 4's loopback, both have weights of 0. Now we can change this, and that's exactly what we're going to do. And you can change it, as I mentioned, on a route by route basis, just like we did with med and just like we did with local pref, with a combination of access lists and route maps. Or we can change it on a per neighbor basis, where with a neighbor command we change the weight for all routes learned from a certain neighbor. And that's the way we're going to do it here. Right now we have weights of 0 for both of the paths to network 4444. But let's just say, and heaven forbid this happen, let's actually take a look at the network selection here, network setup, and this happens. I have been there when these arguments have been held. You'd have one group in AS234 trying to tell AS1, this is the path you're going to use, and the administrator over in AS1 is saying, well, no, this is the path I'm going to use, and they want to use different paths. So what we're looking at right now is a true real-world scenario where the administrator of AS234 has told AS1, hey buddy, when you want to reach anything, when you want to reach the network down there on router 4, you're going to have to use 123.3 as a next hop IP address. And how did they do that? They did that with the MED. And MEDs can be used in unfriendly ways like this on occasion. You could be telling an AS how to enter your administrative system, and they might not even realize it. But in this case, they've realized it. We have realized it. What we want to do as the administrators of AS1 is definitely use the next hop 123.2 as the next hop IP address, and we don't care what AS234 is telling us. We're going to override that, and the only way we can do it is by changing the weight. And you see the default weight is 0, the highest weight's going to be preferred. We can't set a value for below 0. So let's set it to 200. And this is how we're going to do that. Conf T, router BGP 123, router BGP 1. Love those reminders, can't beat that. We're going to name the neighbor first, 172.12.123.2. This is the neighbor that we're going to affect the routes of. And again, we're going to use iOS help. And again, I remind you, you do not need to learn all these to become a CCNP and pass the BSCI exam on the way. And at the very bottom, here's what we're using, the wait command. We're setting the default weight for all routes from this neighbor. And where you simply type that, we're going to set it to 200 and take a look at our BGP routing table as soon as the console message gets done. And let's see if that took effect. Nope, we're going to do a clear IP BGP soft and give it a second here. And you can see already it's already taken place. With that one simple command, we did a couple of things. First off, we changed the weight of this path to 200. That overrides the metric. The metric doesn't even matter anymore because the weight's the first BGP path selection criteria. And you can see now that we are now using 123.2 as the next hop IP address. And it doesn't matter what MED the other side sends us. Doesn't matter because we set the weight, and the weight cannot be beat, it cannot be trumped. We could have set local preference here as well, but we already did that, so I decided we were going to set the weight. And that way we cannot possibly be beaten. So that's the wait command in a nutshell. That's really all there is to it. Just keep in mind a couple of things. It is Cisco proprietary. So in a multi-vendor environment, the local pref value is the one that's going to be changed in this situation. And this change to a route's weight is locally significant only. This router will not advertise this route with a weight of 200. That's very important when it comes to weight because the differences between weight and local pref. When we changed the local preference down in AS234, it was advertised from router 3 to router 4, remember? There's our network again. We changed the local pref here at 3, and that value was advertised to R4. Since we wanted it to be advertised, we needed to use local pref. But if we didn't want it to be advertised for whatever reason, and we just want it to affect the local router, we would then configure weight instead. Let's take a look at that. Let's actually do that in action. I want you to see that in action. We'll go down to router 3 and do a quick show config. See what we need to take off, if anything. Yeah, we're going to take those two statements off there, the route map statements. And thank gosh for the upper key, for the up key. Can't do it here, though. So don't forget, there's a little paste and cut and paste you can do. And you may not be familiar with this. If you do the mark and then just highlight a line or whatever you want to cut, and then right-click on it, you're not going to see anything appear when you do that. But if you go down to where you want to paste it, and then select Paste, look at that. If you didn't know that, you owe me $5 extra. I guess that's really a handy command. And I had actually worked quite a while with Cisco routers before someone showed me that. But again, if you want to cut and paste in a Cisco router, you do a mark just like you do when you're highlighting text, like I've done throughout the course. Right-click on it, the highlight will disappear, and then just go wherever you want to paste it. And there it is, and we'll do the Control A to move to the front, type a neighbor command in, and that's all there is to it. So if you didn't know how to cut and paste, now you do. You can also cut and paste that into Notepad or Word, and it's a really good way to save your sessions, especially if you're working on home lab. Pardon me. If you're working on a home lab from one session to another, you can just cut your entire config or copy your entire config and then just paste it into Notepad, exactly how I showed you there. Just right-click over Notepad and drop it in there. Very handy. Takes a little getting used to the first couple times you do it, but you'll be very happy you learned how to do that after a while. So we did that to prove here that the weight attribute is not going to be advertised when we change it. So we'll do a soft rebound there, or refresh. Go down to router 4 and show IP BGP. And you also see again, here's another route with a weight of 32,768. It's router 4's loopback on router 4. And you see now that the local pref is 100 for all the routes. It's just the way it was before we started. So let's go up to router 3 then and change the weight of all incoming routes from the neighbor, router 1. And we do this and we think, okay, man, we have got it made, and we're going to do a soft reset. And router 4 is going to get these weights and everything's going to be great. But you know it doesn't happen. And I know that I've said a couple of times, sometimes you have to wait a few extra seconds for a change to take effect or to be reflected in your tables. But that new weight's never going to show up because the weight is locally significant only. That's a detail a lot of people tend to forget. And keep that in mind on the exam for scenarios like we've gone through here today. Because everyone's always really tempted to say, oh, well, you know, if we're going to do such and such, let's change the weight attribute because that's the first one considered. Well, yeah, it is the first one considered, but that's not much help if that weight, if that value's got to be carried to other routers. Because if we look at router 3 now, we see the weights of 200. We see that those were successfully changed. But the problem is, if we want router 4 to change its path selection, we're going to have to go to local pref because the weight attribute is not advertised from one router to another. So that is key right there. And I want to make actually a note of that right here on the whiteboard for you, is that the weight attribute is not advertised or sent with updates. It is, everybody say it together, locally significant only. That phrase you got tired of hearing when you were learning about frame relay delcies has come back. So that's the weight attribute in a nutshell. That's really everything you need to know about it. Very simple attribute to work with. Now let's take a look at, like I said, some miscellaneous attributes or some attributes that you'll study more often as you progress through your studies. but you need to know these for the exam. Atomic aggregate, that's a great name. I don't know who was there, I don't know who thought of that, but atomic aggregate. Sounds kind of scary, but trust me, it's not. All it does is indicate the router that performed the route aggregation. And just to refresh your memory, we mentioned at the beginning of this video that aggregation is simply another term for route summarization. We've done it before with other protocols. We're going to do it here again in a few minutes with BGP. Now, the aggregator attribute is a little different. It gives the BGP RID and the AS number of the router that performed the aggregation, and it will also give you a list of the AS numbers that these aggregated routes passed through. Now, the reason we have these to begin with, especially the atomic aggregate, I know when I started studying BGP I thought, well, that's fine, but why do we need that? What this attribute does is it gives notice to downstream routers that more specific BGP routing information was lost at the point of aggregation. Because you have to be really careful with route aggregation with BGP. But this just tells the router, hey, we've got an aggregate route here, and there's some more specific routing information that was lost. And you may hear that and think, well, it's always lost. Because with RIP version 2, we've done route summarization with that. We've done it with EIGRP. You've done it in two different ways with OSPF, with the summary address command and the area range command. You've performed it with IS to IS, and the more specific routing was always lost, right? Remember that only the summary address was advertised, and the more specific routes were not? Well, maybe that's not the case with BGP route aggregation. And before we start talking about that, the community attribute allows us to logically group routers that have a common configuration. It makes them members of a community. And creating BGP communities can save you a great deal of work. And I will give you an example of that before the end of the BGP series here. I'd like you to see a BGP community. You basically need to know for purposes of the exam that these three attributes exist and what they do, but you're not going to be asked to work with them. They're not going to ask you to create a BGP community on the exam, most likely. But in the off chance that they do, I'm going to show you one before the end of the course. But right now, we are going to talk about route aggregation. Boy, that's a pretty empty screen for route aggregation, right? But the big important fact about route aggregation is right there on the screen. By default, both the route aggregate and the more specific routes are advertised. That's totally opposite from RIP version 2, EIGRP, IS to IS, and OSPF. Because when we configured route summarization with those 4 or 5 protocols, then we saw the summary route in the downstream router tables, but we certainly didn't see the more specific routes. That would kind of defeat the purpose. But by default, BGP route aggregation advertises the aggregate and the more specific routes. We have the choice, though, of changing that default to advertise only the aggregate or the aggregate and some of the more specific routes. We're only going to look at the first 2 here in this course because you're not going to be asked anything about advertising an aggregate route and some of the more specific routes. That's not going to happen. So to see route aggregation in process, to see the default and see how we change the default, we're still going to use the same network setup that we have. And we're going to go to router 1, create 4 loopbacks, but not with 32-bit masks, and then advertise them into BGP, and then go downstream and see what router 2 and router 3 end up seeing. So let's just go up to router 1. It never hurts to look at your configuration to see what loopbacks you've already got. So we've got quite a few here, but we're going to raise the numbers here a little bit. We'll put a loopback 16 on. We'll put a loopback 17 on. We're going to use 8-bit masks for these. And then finally 19. If you think I have an ulterior motive for these addresses, you know me pretty well by now. And you can already start summarizing them if you want to, because I'm going to put them into BGP with the network command. Mask. I get so used to that. Let's slow down. There we go. And just a couple more here. One more to go. And that's it. So we're going to clear our BGP process right after the console message interrupts me. With a soft reset, we'll do a WR, and we're going to go down to router 2, take a look at the BGP table. And let's see if we see them yet. Not yet. Let's give them just another couple seconds here to show up. We're looking for networks 16, 17, 18, and 19. Not quite yet. And there they go. Just about the time you start wondering if you did it right, that's when they're going to show up. So, we first off do our basic check here. We see that we have an asterisk and an arrowhead, which means that the paths are not just valid, but they are best paths. They are in use. And there's nothing wrong with this. But again, BGP can always benefit from route aggregation, just as our IGPs can benefit from route summarization. Helps keep the network tables smaller, the routing tables smaller but concise. So if you've already done the summarization on paper, fantastic. If not, take a quick minute to take a look at that and see how you would handle that, because you better be ready to do that kind of thing on the exam. We have the networks 16 through 19 for first octets put into BGP. And you need to be able to look at that and say, okay, here's the summary address. That one's very straightforward stuff. We'll walk through that right here, actually. And we just need to put the first octet here, because we obviously know that the last octets are all zeros. So what does 16 look like in binary? The 16-bit there is set, none of the others are. And that's 19. So again, route summarization, just as we've done in earlier videos. Summarization, aggregation, same thing. We work from left to right, and we determine at what point the 4 routes in question no longer have a bit in common. And it's right there. So we simply add the value of the bits to the left-hand side of that line, and that is 16, since that's the only bit that's set. So we know it's going to be 16,000. Everything else is going to be a 0. Now we have to determine the summary or the aggregate mask. And again, just as we've done earlier, practice makes perfect. We have a 1 for all the bits on the left-hand side of that line and a 0 for all the bits on the right. And then we simply add that up, and it comes to 252,000. Nothing to it when you know how, and I know that you know how. So now we have the route, and everything's fantastic, and now you just have to know the right command. So we do a conf t, router BGP1, and the correct command is aggregate address. And we follow that just as we did with the other summary address and area range commands an IP summary address rep. I mean, every protocol's got its own command there. And that should do it. But this is interesting. At the end of this, we've got a lot of possible options that iOS help shows us. And again, this isn't something that you've got to know all this stuff for the BSCI. But when you're working in a home lab, you really should get used to using iOS help even when you think there aren't going to be any other options. It's a great way to learn firsthand. I've picked up a lot of interesting knowledge that way, just playing with iOS help. But let's see if any of those are going to come back on us, if we're going to use any of those later. Because there's the aggregate, and we clear our BGP settings with clear IP BGP asterisk soft. We'll go to a downstream router, router 2 in this case. And with all the IGPs that we've configured so far, RIP, IGRP, not IGRP, excuse me, RIP version 2, EIGRP, OSPF, IS-IS, all those protocols, when you configure a summary route and then you go to a downstream router, the only route you expect to see is the summary route. You don't expect to see the routes that you summarize. That's the whole point. Let's look at the BGP table here. Have we gotten the aggregate? Yeah, this is interesting. We have the aggregate. You see it there, 16.000/6. And of course, you know that's prefix notation. And that number represents the number of ones that lead off the mask. But look at that. We also have the summarized or aggregated routes. They're still advertised, and this is the default. And boy, come exam day, you better remember that one, because it's very unusual. If you haven't actually seen that on routers, you probably wouldn't know it. Very unusual default for BGP in this regard. So we better know how to send out the summary only. And the reason I say it that way is because we're going to use the summary only option that we saw up here in iOS help. When we were looking at the aggregate address command and we ran iOS help, the one that we're looking at is called summary only, and right there it tells us what it's going to do. It filters the more specific routes from the updates. So we better know what the default is, and we better know how to get around that default. That's a good idea. So we're going to go back up to router 1. What I recommend you do is remove the aggregate address command. Up arrow, Control A, no space. And now we're going to put in the full command. And we can actually up arrow and save a little bit of typing there. Aggregate address 16.000.252.0.0.0. There's nothing wrong with using the up arrow, or obviously I wouldn't be showing it to you. But a lot of times when you're first learning these commands, typing them out a couple of times is a great way to retain them for exam day. Because then you're dealing with a lot of multiple choice, and that's not always the easiest thing to do. Summary only. That's the key. Soft. Right on the way out. Let's go down to router 2, see if we have the deal here. Show IP BGP. And we have now the summary address only. We do not have the more specific routes. You can see right down there at the bottom. That's generally what you're going to want, especially you need to know how to do it for the exam and for the real world. But as you're going to see, as you progress through your studies and you hit more and more difficult and complex BGP scenarios, and as a friend of mine likes to say, is there another kind? You want to be careful with aggregation in the real world, because there is a reason that the default with BGP actually lets the more specific routes through. So be careful with that. I would not rush out and implement that in a production network just because you saw it there. If you're working with BGP and you make a mistake, you can cripple internet connectivity actually for some people around the world. That has happened before. So it's not something we want to rush into the office and say, hey, I know how to aggregate these routes now. So we just need to be careful with that. But particularly for exam day, know what the default is, know the command to get around it, And then finally, in this part of the video, something else to keep in mind is simply resetting the peer connections. And the soft reset is a more recent invention of Cisco, and it's great because in the ancient times, you had to do a hard reset. And you've already seen that in action, but we'll just do one right here. If we run clear IP BGP asterisk and hit enter, we're going to lose our adjacencies. You could see those adjacencies came down very quickly, and hopefully they'll come back up pretty shortly, but it could take 30 to 40 seconds, and that may not be something we want to do. It probably isn't if we're at work. So they've come up with that soft reset. Let's see what iOS Help has to say about that. Okay, we've got all kinds of options now with clearing the IP BGP connections. But when you do soft, it's a soft reconfig, and it resets the connection without tearing it down. And that way we don't lose connectivity. It's the equivalent, really, of clear IP route asterisk for BGP. Because what you're really doing that for is to update your routing tables without actually tearing the connections down. So it's a good thing to keep that in mind as well when it comes to the peer connections, how to refresh them without tearing them down. But when you accidentally do clear IP BGP asterisk and you forget the soft part, don't be too hard on yourself because it happens to everybody.